Hey everyone, this is the chapter 4 and 5 review video. In this video, we're going to go over Newton's laws, how to draw free body diagrams, how to set up Newton's second law, and how to incorporate friction in our problems. First, Newton's laws. The first law is the law of inertia. An object in motion stays in motion, an object at rest stays at rest, unless acted upon by an unbalanced force. Let's look at a question. True or false? There must be an unbalanced force acting on a moving object. This is actually false. If the object is moving, you don't need any force acting on it to keep moving. It will keep moving in a straight line at a constant speed. The unbalanced force actually changes its motion. The second law is the sum of all the forces is equal to ma. You'll often see it as A equals F over m. Let's look at a question. If you have 2 times the mass, then you're actually going to have 1/2 of the accelerations. When you write it as A equals F over m, you can see that better. Twice the mass is half the acceleration. We'll talk about how to use Newton's second law later in this video. The third law is the law of action and reaction. For every force, there's an equal and opposite reaction. We can write this law as FAB equals negative BA. What this tells us is that the forces are acting on different objects. The force acting from A acting on B is equal to the negative of the force from B acting on A. The negative tells us that the forces are in opposite directions. Let's look at an example. What is the reaction force to your weight? A lot of people say it's the normal force, but actually it isn't. Let's take you right here. Your weight is going straight down. The weight is the force from the earth pulling on the object. Let's call the object M. So according to this law, the reaction force, to find it, you're just going to switch the subscripts. The reaction force is going to be the force from the mass pulling up on the earth. We just switch the subscripts. The forces are going in opposite directions. That's how to find the reaction force. Make sure the forces are acting on different objects. Next, how to draw free body diagrams. Let's look at all the different forces that we might encounter. First, the weight. We're going to write this as W or F sub G. We're going to include weight in our free body diagram always. And the direction will always be straight down. So this is the easiest force to draw. For example, let's say we have an object that's just falling down. The free body diagram, we're going to draw a box. We're going to draw an arrow going straight down, label it W for weight. Tension, we're going to call it T or F sub T. We're going to include it when there's a rope or string in the problem. The direction is always away from the object. For example, let's say there's an object hanging from a string attached to a wall. When we draw the free body diagram for the object, we draw the object, we draw the tension going up, away from the object along the string, and the weight is still straight down. Always include the weight. Next, normal force. We'll call it N or F sub N. We're going to include it whenever there's a surface. The direction will be perpendicular and away from the surface. For example, let's say we have an object on an incline. We're going to draw the object and the incline. We're going to draw a force away from and perpendicular to the incline. That's going to be the normal force. The weight is still going to be straight down. Next is the applied force. We'll call it F sub A, but it can be called anything in the problem. We're going to include it when the problem specifically mentions that there's a push or pull or some kind of applied force acting on the object. The direction will usually be given. For example, let's say somebody is pulling an object at an angle here. They're moving to the right. So the force is at an angle. That's an applied force going at an angle, which would usually be given, and you'd know exactly what the angle would be. Now, because this object is on a surface, we still have a normal force going perpendicular from the surface and a weight going straight down. Finally, friction that we'll talk about at the end of this video. There's kinetic or static friction, FK or FS. We're going to include it when we know that there's a rough surface. The direction is going to be parallel to the surface and opposing the motion or opposing the attempted motion. For example, let's say that an object is sliding down an incline. There is motion in this case, so that would be kinetic friction. It's going to be parallel to the incline and opposing the motion. So that kinetic friction force will be up and to the right. So this is how you draw free body diagrams, and you know which way to draw all the forces acting on the object. This is going to be very useful when setting up Newton's second law problems. But first, we need to know a few more things. You have to be able to recognize when you're in equilibrium. Keywords in a problem that tell you that you're in equilibrium is when you are at rest or moving at a constant velocity. When you see these keywords in a problem, you want to think equilibrium, and then you want to think the sum of all the forces is equal to 0. This is going to help you solve the problem. For example, let's say the crate is moving at a constant speed. What is the applied force? Well, because we are moving at a constant speed and we're going to assume we're moving in a straight line, that means we're moving at a constant velocity. We know we are in equilibrium, the sum of all the forces is equal to 0. That means that the applied force must perfectly balance the friction force. The applied force is going to have to go to the right in order to balance the friction force going to the left. Sometimes there'll be a question asking for the apparent weight. The apparent weight is typically a normal force or a tension force. If somebody's on the ground, it's going to be a normal force. If an object is hanging from a string or a scale, it will be a tension force. The apparent weight is how heavy you feel. If you're in an elevator and it's not moving, you're going to feel your normal weight. If you're in an elevator accelerating upward, you're going to feel a weight greater than your normal weight. That would be your apparent weight. If you are in an elevator accelerating downward, you're going to feel less than your regular weight. Let's look at an example. True or false? When moving downward at a constant speed in an elevator, your weight reading on a scale is less than your normal weight. So you might think, oh, well, we just said that when you're accelerating downward, you're less than your normal weight. But read the words carefully. It says that you're moving downward at a constant speed. Assuming in a straight line, that means you are going at a constant velocity. That means you think equilibrium in your head, and you know the forces are actually going to balance. So draw your free body diagram. This is you. This is the normal force acting on you because you're on the floor or the scale. This is the weight. There's no acceleration, so the force is perfectly balanced. The normal force going up is positive, the weight going down is negative. Those two forces will balance, equal to 0, and that means that your normal force, which is the weight reading, which is your apparent weight, is equal to your actual weight. What about if an object is on an incline? The first thing you're going to want to do is rotate the x and y coordinate system. Instead of the x-axis being horizontal, the x-axis will be parallel to the surface, and the y-axis will be perpendicular to the surface. So what happens is when you draw the weight going straight down, that weight will have an x and a y component. The y component will be perpendicular to the surface. The x component will be parallel to the surface. The little angle up here will be the same angle as the incline angle. So that means your weight has an x and a y component, which you can find using the trig functions. The x component will use the sine function because it's opposite the angle, and the y component will use the cosine function because it's adjacent to the angle. You will have to substitute these components into your Newton's second law equations when you are solving problems with objects on an incline. And finally, when you have connected objects, remember, these two objects are connected by one string, so there's only one tension in that string. There's a tension up away from the object for M1, there's a tension up away from the object for M2. Both of these tensions are the same. Likewise, the acceleration is the same. The magnitude of the acceleration is the same. They're going in opposite directions, but the amount of acceleration is the same. When you're solving a problem with connected objects, we'll do so in a minute, you will draw a separate free body diagram for each one, but keep in mind that the tension and the acceleration is the same for each mass. Finally, how do we solve for friction force? We have kinetic friction when an object is moving. Let's say an object is moving to the right, there's going to be that kinetic friction to the left opposing that motion. When solving for kinetic friction force, we can always use the equation F sub k equals mu k times n, where mu k is the coefficient of kinetic friction and n is the normal force. We can only use the equilibrium condition, the sum of Fx equals 0, when there's an indication, as we said earlier, that you are moving at a constant velocity. So we have these two different equations that we can use to solve for kinetic friction force. If we're not moving, we're at rest, we have static friction in the problem. Now, as we said earlier, both of these things happen when we have a rough surface. Let's say we have a force trying to pull this object to the right. The static friction force is just going to oppose it. To find the static friction force, because we are at rest, we can always use the equilibrium condition that the sum of the forces in the x direction equals 0. We can only use the equation to find the maximum static friction force equals mu s times n. We can only use this when there's some indication that we're on the verge of slipping. That means that there's some indication in the problem that the object is about to move. In that case, we are able to use this equation if it's helpful to us. Let's do an example. A 10-kilogram box is initially at rest. Will the box move due to an applied force Fa equals 25 newtons? We see in the picture that the applied force is horizontal. First thing you want to do, draw the free body diagram. You always have a weight going straight down. We have a normal force perpendicular to the surface. We have a friction force opposing the motion, or if it's not moving, opposing the attempted motion. So right now we don't know if it's moving or not, so we'll just write a lowercase f. In order to find out if the box will move, we need to calculate the maximum static friction force using the equation Fs max is mu s times n. We can calculate this force to see how much force does it take for the object to be on the verge of slipping. So we're not saying we're on the verge of slipping, we're just going to calculate this number. Now, to find n, do not automatically write down n is equal to mg. Always set up the sum of the forces in the y direction equal to 0, since we know we're in equilibrium in the y direction. So the normal force minus the weight equals 0, and this does tell us that for this case, the normal force will equal the weight. So let's plug in the mu s times mg. We're going to plug in the numbers 0.4 times 10 times 9.8. That's going to give us a maximum static friction force of 39.2 newtons. But the applied force was only 25 newtons. So that means that this applied force is not large enough. We're not going to be on the verge of slipping. We're not going to be moving. The answer is no, we're not going to be moving. Now, if the question asked for what is the friction force acting on the object, we know it's a static friction force. Do not say the answer is 39.2 because we are not on the verge of slipping. To find a static friction force when we're not on the verge of slipping, we said that we can use the equilibrium condition in the x direction. The sum of the forces in the x direction equals 0. The Fa is going to perfectly balance the static friction force. So that means the static friction force will equal 25 newtons. The static friction force would increase to match the applied force until it reached a value of 39.2 newtons. After that point, the object is going to be on the verge of slipping, and any force greater than 39.2 would cause the object to start moving. Let's look at one final example that puts all of this together. We have two objects connected on an incline, and there is friction on the incline because we have a rough surface. We're looking for the normal force on M1. First thing you want to do is draw the free body diagram. We have a weight going straight down. We have a normal force perpendicular to the surface. We have a tension pulling away from the object. We have a friction force away from the motion. It's kinetic friction since we're moving. Because we're in an incline, we have that rotated coordinate system, so we're going to draw the y component and the x component of the weight going down and to the left, respectively. Now that we have done all of this, we can go ahead and set up Newton's second law separately in the x and the y directions. Since we're looking for normal force, we care about a force in the y direction since we have that rotated coordinate system. In the y direction, we know that we're in equilibrium because we're not jumping up and down. Whenever we're sliding along a surface, we'll always be in equilibrium in the y direction. So the normal force will be positive since it's going up, Wy will be negative since it's going down. Those are the only forces in the y direction we set it equal to 0. This means that the normal force equals mg cosine theta. That's it, we're done with this problem. We had a lot of extra information. The purpose of the extra information was just to show you how to set up the Newton's second law in the other direction if we needed to. Let's say we needed to set it up in the x direction. The sum of the forces in the x direction would equal ma. Let's pick a direction. What's positive and what's negative? Let's call the positive direction the direction of the acceleration. That means Wx is positive and tension and friction force are negative. We're going to have Wx minus tension minus Fk equals ma. If we had to expand on that, we could put in the definition of Wx, which is mg sine theta, and we could put in the definition of the friction force, which is mu k times n. All of this would equal ma. If we needed to solve further, we could even plug in the normal force that we found into that equation. Finally, for M2, you want to be able to set up Newton's law for that as well. Let's draw the free body diagram. There's a tension going up and there's a weight going down. Oh, before I do this, I forgot to specify that we were talking about M1 the whole time here. So don't forget the subscript for M1 because now we're talking about M2. For M2, there's going to be an acceleration upwards since M1 is going down over here. So we're going to call tension going up positive, weight going down negative. The sum of all the forces in the y direction will equal m2a. We're going to have T minus W equals m2a, and we can simplify this further by saying T minus m2g equals m2a. And this is a good example of how to set up Newton's second law when we have friction and connected masses. That's all for this review video.